So I want to talk quickly about complex roots, okay? Because there's some symmetry here also, right? So before I begin, I want to talk quickly about the idea of a complex conjugate, okay? So the last time we talked about complex numbers having this form. So they have a real part A and an imaginary part B times the imaginary number I, okay? This combination is a complex number, and you can plot it in the complex plane, or the Argand diagram as it's sometimes known. But there is the idea of a complex conjugate, okay, and it's very simple. You just take the imaginary part and you multiply it by minus. So the conjugate would be z with a bar over it like this, is a minus bi, okay? And it's important, in fact it's very important within the realm of complex numbers, this idea of a conjugate. It'll pop up again and again. So we're just going to use it to examine symmetries in complex roots at the moment. Okay. So let's begin with a simple example. If you have the square root of 4, okay, the answer, there are two answers, and they come in kind of pairs like this, plus or minus 2, right? These answers are real, okay? There's no complex solutions to this, but they come in pairs nevertheless. You can plot them on the Argand diagram, and they're just both on the real axis there. Okay. Good, and the reason is that whether or not you choose plus or minus 2, if you square it, you'll get 4. Okay. Now, in the next example, we're going to take the cube root of 8. Now, I'm not going to go through how we find these complex solutions. It's not very complicated, but I just want to concentrate on the symmetries at the moment, so I'm not interested in finding roots per se. But you can verify that these are in fact cube roots by cubing these expressions and finding out what they produce. Okay? Well, if you go through the process, you'll find that the cube root of 8 is plus 2, and then a complex conjugate pair, minus 1 plus or minus the square root of 3 times I. If you plot it on the Argand diagram, you get an equilateral triangle. Okay, so it's quite beautiful to look at in that context. So you have the plus 2 root here, and then the twin pairing here. Just vertical, one from the other. Okay, you'll notice that with the square root of 4 there were 2 answers, and with the cube root of 8 there are 3. This highlights a general rule in mathematics, okay, which we'll come to in a moment. Yes, you could of course restrict yourself to real solutions, and that's what we normally do. But if you allow complex solutions, you get this these patterns emerge. Okay, let's take one more example. This is the 4th root of 16. Okay, and if you go through the mathematics, you'll find that there's a real pair, plus or minus 2, and a complex conjugate pair, plus or minus 2i. And this forms a perfect square in the Argand diagram. Okay, so the first thing you should notice is this rule here. Every number has nth roots. So the square root has 2 solutions, the cube root has 3 solutions, and the 4th root has 4 solutions. Okay, with a maximum of 2 real roots, and complex roots come in conjugate pairs. Okay, the reason it displays this symmetry is because it doesn't matter if you take minus 2 or plus 2. If you make it to the power of 4, both answers will give you 16. And the same is true of the complex conjugate pairs. It doesn't matter which one you take, but if you take 2i to the 4th power or minus 2i to the 4th power, you'll get that 16. So it always the solutions always appear in these pairs, real and complex. Okay, and that's what gives rise to these symmetries in the Argand diagram. The reason there are only 2 real roots ever is you can see from the diagrams, okay? These form shapes that can cut the x-axis at a maximum of 2 points, okay? And this, I should say, follows this pattern continuing up. So if you take the fifth root, it will form a pentagon. If you take the sixth root, it will form a hexagon, and so on. So it will form n-gons as you move up into higher and higher roots. Okay, but you can see no matter what shape you get, it can cut the x-axis at a maximum of 2 points. So that's why you get only 2 real roots. And the complex roots always come in the conjugate pairs, as I say, because it doesn't matter which you take, the conjugate or the original, they'll both give you the desired result.